Algorithms to Live by the Computer Science of Human Decisions. Author, Brian Christian and Tom Griffiths. 5 Scheduling First Things First. How we spend our days is, of course, how we spend our lives. Annie Dillard. Why don't we write a book on scheduling theory? I asked. It shouldn't take much time. Book writing, like war making, often entails great miscalculations. 15 years later, scheduling is still unfinished. Eugene Lawler. It's Monday morning, and you have an as yet blank schedule and a long list of tasks to complete. Some can be started only after others are finished. You can't load the dishwasher unless it's unloaded first, and some can be started only after a certain time. The neighbors will complain if you put the trash out on the curb before Tuesday night. Some have sharp deadlines, others can be done whenever, and many are fuzzily in between. Some are urgent, but not important. Some are important, but not urgent. We are what we repeatedly do. You seem to recall Aristotle saying whether it's mop the floor, spend more time with family, file taxes on time, learn French. So what to do, and when, and in what order. Your life is waiting. Though we always manage to find some way to order the things we do in our days, as a rule we don't consider ourselves particularly good at it, hence the perennial bestseller status of time management guides. Unfortunately, the guidance we find in them is frequently divergent and inconsistent. Getting things done advocates a policy of immediately doing any task of 2 minutes or less as soon as it comes to mind. Rival bestseller Eat That Frog advises beginning with the most difficult task and moving toward easier and easier things. The Now Habit suggests first scheduling one's social engagements and leisure time and then filling the gaps with work rather than the other way around, as we so often do. William James, the father of American psychology, asserts that there's nothing so fatiguing as the eternal hanging on of an uncompleted task, but Frank Partnoy, in Wait, makes the case for deliberately not doing things right away. Every guru has a different system, and it's hard to know who to listen to. Spending time becomes a science. Though time management seems a problem as old as time itself, the science of scheduling began in the machine shops of the Industrial Revolution. In 1874, Frederick Taylor, the son of a wealthy lawyer, turned down his acceptance at Harvard to become an apprentice machinist at Enterprise Hydraulic Works in Philadelphia. 4 years later, he completed his apprenticeship and began working at the Midvale Steel Works, where he rose through the ranks from lathe operator to machine shop foreman, and ultimately to chief engineer. In the process, he came to believe that the time of the machines and people he oversaw was not being used very well, leading him to develop a discipline he called scientific management. Taylor created a planning office, at the heart of which was a bulletin board displaying the shop's schedule for all to see. The board depicted every machine in the shop, showing the task currently being carried out by that machine and all the tasks waiting for it. This practice would be built upon by Taylor's colleague Henry Gantt, who in the 1910s developed the Gantt charts that would help organize many of the 20th century's most ambitious construction projects, from the Hoover Dam to the interstate highway system. A century later, Gantt charts still adorn the walls and screens of project managers at firms like Amazon, IKEA, and SpaceX. Taylor and Gantt made scheduling an object of study, and they gave it visual and conceptual form. But they didn't solve the fundamental problem of determining which schedules were best. The first hint that this problem even could be solved wouldn't appear until several decades later, in a 1954 paper published by Rand Corporation mathematician Selma Johnson. The scenario Johnson examined was bookbinding, where each book needs to be printed on one machine and then bound on another. But the most common instance of this two-machine setup is much closer to home: the laundry. When you wash your clothes, they have to pass through the washer and the dryer in sequence, and different loads will take different amounts of time in each. A heavily soiled load might take longer to wash, but the usual time to dry. A large load might take longer to dry, but the usual time to wash. So, Johnson asked, if you have several loads of laundry to do on the same day, what's the best way to do them? His answer was that you should begin by finding the single step that takes the least amount of time, the load that will wash or dry the quickest. If that shortest step involves the washer, plan to do that load first. If it involves the dryer, plan to do it last. Repeat this process for the remaining loads, working from the two ends of the schedule toward the middle. Intuitively, Johnson's algorithm works because regardless of how you sequence the loads, there's going to be some time at the start when the washer is running, but not the dryer, and some time at the end when the dryer is running, but not the washer. By having the shortest washing times at the start and the shortest drying times at the end, you maximize the amount of overlap when the washer and dryer are running simultaneously. Thus you can keep the total amount of time spent doing laundry to the absolute minimum. Johnson's analysis had yielded scheduling's first optimal algorithm: start with the lightest wash, end with the smallest hamper. Beyond its immediate applications, Johnson's paper revealed two deeper points. First, that scheduling could be expressed algorithmically, and second, that optimal scheduling solutions existed. This kicked off what has become a sprawling literature, exploring strategies for a vast menagerie of hypothetical factories with every conceivable number and kind of machines. We are going to focus on a tiny subset of this literature, the part that, unlike bookbinding or laundry, deals with scheduling for a single machine. Because the scheduling problem that matters the most involves just one machine, ourselves. Handling deadlines. With single machine scheduling, we run into something of a problem right off the bat. Johnson's work on bookbinding was based on minimizing the total time required for the two machines to complete all of their jobs. In the case of single machine scheduling, however, if we are going to do all the tasks assigned, then all schedules will take equally long to complete. The order is irrelevant. This is a sufficiently fundamental and counterintuitive point that it's worth repeating. If you have only a single machine, and you're going to do all of your tasks, then any ordering of the tasks will take you the same amount of time. Thus we encounter the first lesson in single machine scheduling literally before we even begin. Make your goals explicit. We can't declare some schedule a winner until we know how we are keeping score. This is something of a theme in computer science. Before you can have a plan, you must first choose a metric. And as it turns out, which metric we pick here will directly affect which scheduling approaches fare best. The first papers on single machine scheduling followed quickly on the heels of Johnson's bookbinding work and offered several plausible metrics to consider. For each metric, they discovered a simple, optimal strategy. It is of course common. For instance, for tasks to have a due date, with the lateness of a task being how far it has gone overdue. So we can think of the maximum lateness of a set of tasks as the lateness of whatever task has gone furthest past its due date, the kind of thing your employer might care about in a performance review, or what your customers might care about in a retail or service setting, where the maximally late task corresponds to the customer subjected to the longest wait time. If you're concerned with minimizing maximum lateness, then the best strategy is to start with the task due soonest and work your way toward the task due last. This strategy, known as earliest due date, is fairly intuitive. For instance, in a service sector context, where each arriving patron's due date is effectively the instant they walk in the door, it just means serving customers in order of arrival. But some of its implications are surprising. For example, how long each task will take to complete is entirely irrelevant. It doesn't change the plan, so in fact you don't even need to know. All that matters is when the tasks are due. You might already be using earliest due date to tackle your workload, in which case you probably don't need computer science to tell you that it's a sensible strategy. What you may not have known, though, is that it's the optimal strategy. More precisely, it is optimal assuming that you're only interested in one metric in particular, reducing your maximum lateness. If that's not your goal, however, then another strategy might be more applicable. For instance, consider the refrigerator. If you're one of the many people who have a community-supported agriculture (CSA) subscription, then every week or two you've got a lot of fresh produce coming to your doorstep all at once. Each piece of produce is set to spoil on a different date, so eating them by earliest due date, in order of their spoilage schedule, seems like a reasonable starting point. It's not, however, the end of the story. Earliest due date is optimal for reducing maximum lateness, which means it will minimize the rottenness of the single most rotten thing you'll have to eat. That may not be the most appetizing metric to eat by. Maybe instead we want to minimize the number of foods that spoil. Here a strategy called Moore's algorithm gives us our best plan. Moore's algorithm says that we start out just like with earliest due date by scheduling out our produce in order of spoilage date, earliest first, one item at a time. However, as soon as it looks like we won't get to eating the next item in time, we pause, look back over the meals we've already planned, and throw out the biggest item, that is, the one that would take the most days to consume. For instance, that might mean foregoing the watermelon. That would take a half dozen servings to eat. Not even attempting it will mean getting to everything. That follows a lot sooner. We then repeat this pattern, laying out the foods by spoilage date, and tossing the largest already scheduled item anytime we fall behind. Once everything that remains can be eaten in order of spoilage date without anything spoiling, we've got our plan. Moore's algorithm minimizes the number of items you'll need to throw away. Of course, you're also welcome to compost the food, donate it to the local food bank, or give it to your neighbor. In an industrial or bureaucratic context, where you can't simply discard a project, but in which the number rather than the severity of late projects is still your biggest concern, Moore's algorithm is just as indifferent about how those late tasks are handled. Anything booted from the main portion of your schedule can get done at the very end, in any order. It doesn't matter, as they're all already late. Getting things done. Do the difficult things while they are easy, and do the great things while they are small. Laotzu. Sometimes due dates aren't our primary concern and we just want to get stuff done, as much stuff, as quickly as possible. It turns out that translating this seemingly simple desire into an explicit scheduling metric is harder than it sounds. One approach is to take an outsider's perspective. We've noted that in single machine scheduling, nothing we do can change how long it will take us to finish all of our tasks, but if each task, for instance, represents a waiting client, then there is a way to take up as little of their collective time as possible. Imagine starting on Monday morning with a 4-day project and a 1-day project on your agenda. If you deliver the bigger project on Thursday afternoon, 4 days elapsed, and then the small one on Friday afternoon, 5 days elapsed, the clients will have waited a total of 4 plus 5 equals 9 days. If you reverse the order, however, you can finish the small project on Monday and the big one on Friday, with the clients waiting a total of only 1 plus 5 equals 6 days. It's a full work week for you either way, but now you've saved your clients 3 days of their combined time. Scheduling theorists call this metric the sum of completion times. Minimizing the sum of completion times leads to a very simple optimal algorithm called shortest processing time. Always do the quickest task you can. Even if you don't have impatient clients hanging on every job, shortest processing time gets things done. Perhaps it's no surprise that it is compatible with the recommendation in getting things done to immediately perform any task that takes less than 2 minutes. Again, there's no way to change the total amount of time your work will take you, but shortest processing time may ease your mind by shrinking the number of outstanding tasks as quickly as possible. Its sum of completion times metric can be expressed another way. It's like focusing above all on reducing the length of your to-do list. If each piece of unfinished business is like a thorn in your side, then racing through the easiest items may bring some measure of relief. Of course, not all unfinished business is created equal. Putting out an actual fire in the kitchen should probably be done before putting out a fire with a quick email to a client, even if the former takes a bit longer. In scheduling, this difference of importance is captured in a variable known as weight. When you're going through your to-do list, this weight might feel literal, the burden you get off your shoulders by finishing each task. A task's completion time shows how long you carry that burden. So minimizing the sum of weighted completion times, that is, each task's duration multiplied by its weight, means minimizing your total oppression as you work through your entire agenda. The optimal strategy for that goal is a simple modification of shortest processing time. Divide the weight of each task by how long it will take to finish, and then work in order from the highest resulting importance per unit time. Call it density if you like, to continue the weight metaphor, to the lowest. And while it might be hard to assign a degree of importance to each one of your daily tasks, this strategy nonetheless offers a nice rule of thumb. Only prioritize a task that takes twice as long if it's twice as important. In business contexts, weight might easily be translated to the amount of money each task will bring in. The notion of dividing reward by duration translates, therefore, to assigning each task an hourly rate. If you're a consultant or freelancer, that might in effect already be done for you. Simply divide each project's fee by its size, and work your way from the highest hourly rate to the lowest. Interestingly, this weighted strategy also shows up in studies of animal foraging, with nuts and berries taking the place of dollars and cents. Animals, seeking to maximize the rate at which they accumulate energy from food, should pursue foods in order of the ratio of their caloric energy to the time required to get and eat them, and indeed appear to do so. When applied to debts rather than incomes, the same principle yields a strategy for getting in the black that's come to be called the debt avalanche. This debt reduction strategy says to ignore the number and size of your debts entirely and simply funnel your money toward the debt with the single highest interest rate. This corresponds rather neatly to working through jobs in order of importance per unit time. And it's the strategy that will reduce the total burden of your debt as quickly as possible. If, on the other hand, you're more concerned with reducing the number of debts than the amount of debt, if, for instance, the hassle of numerous bills and collection phone calls is a bigger deal than the difference in interest rates, then you're back to the unweighted, just get stuff done flavor of shortest processing time, paying off the smallest debts first simply to get them out of the way. In debt reduction circles, this approach is known as a debt snowball. Whether people, in practice, ought to prioritize lowering the dollar amount of their debts or the quantity of them remains an active controversy, both in the popular press as well as in economics research. Picking our problems. This brings us back to the note on which we began our discussion of single machine scheduling. It's said that a man with one watch knows what time it is, a man with two watches is never sure. Computer science can offer us optimal algorithms for various metrics available in single machine scheduling, but choosing the metric we want to follow is up to us. In many cases, we get to decide what problem we want to be solving. This offers a radical way to rethink procrastination, the classic pathology of time management. We typically think of it as a faulty algorithm. What if it's exactly the opposite? What if it's an optimal solution to the wrong problem? There's an episode of The X-Files where the protagonist Mulder, bedridden and about to be consumed by an obsessive-compulsive vampire, spills a bag of sunflower seeds on the floor in self-defense. The vampire, powerless against his compulsion, stoops to pick them up one by one, and ultimately the sun rises before he can make a meal of Mulder. Computer scientists would call this a ping attack or a denial of service attack. Give a system an overwhelming number of trivial things to do, and the important things get lost in the chaos. We typically associate procrastination with laziness or avoidance behavior, but it can just as easily spring up in people, or computers, or vampires, who are trying earnestly and enthusiastically to get things done as quickly as possible. In a 2014 study led by Penn State's David Rosenbaum, for example, participants were asked to bring either one or two heavy buckets to the opposite end of a hallway. One of the buckets was right next to the participant, the other was part way down the hall. To the experimenter's surprise, people immediately picked up the bucket near them and lugged it all the way down, passing the other bucket on the way, which they could have carried a fraction of the distance. As the researchers write, this seemingly irrational choice reflected a tendency to procrastinate, a term we introduced to refer to the hastening of sub-goal completion, even at the expense of extra physical effort. Putting off work on a major project by attending instead to various trivial matters can likewise be seen as the hastening of sub-goal completion, which is another way of saying that procrastinators are acting optimally to reduce as quickly as possible the number of outstanding tasks on their minds. It's not that they have a bad strategy for getting things done, they have a great strategy for the wrong metric. Working on a computer brings with it an additional hazard when it comes to being conscious and deliberate about our scheduling metrics. The user interface may subtly, or not so subtly, force its own metric upon us. A modern smartphone user, for instance, is accustomed to seeing badges hovering over application icons, ominous numbers in white on red signaling exactly how many tasks each particular app expects us to complete. If it's an email inbox blaring the figure of unread messages, then all messages are implicitly being given equal weight. Can we be blamed, then, for applying the unweighted shortest processing time algorithm to the problem, dealing with all of the easiest emails first, and deferring the hardest ones till last to lower this numeral as quickly as Possible? Live by the metric, die by the metric. If all tasks are indeed of equal weight, then that's exactly what we should be doing. But if we don't want to become slaves to minutiae, then we need to take measures toward that end. This starts with making sure that the single machine problem we are solving is the one we want to be solving. In the case of app badges, if we can't get them to reflect our actual priorities and can't overcome the impulse to optimally reduce any numerical figure thrown in our face, then perhaps the next best thing is simply to turn the badges off. Staying focused not just on getting things done, but on getting weighty things done, doing the most important work you can at every moment, sounds like a surefire cure for procrastination. But as it turns out, even that is not enough. And a group of computer scheduling experts would encounter this lesson in the most dramatic way imaginable on the surface of Mars, with the whole world watching. Priority inversion and precedence constraints. It was the summer of 1997, and humanity had a lot to celebrate. For the first time ever, a rover was navigating the surface of Mars. The $150 million Mars Pathfinder spacecraft had accelerated to a speed of 16,000 miles per hour, traveled across 309 million miles of empty space, and landed with space-grade airbags onto the rocky red Martian surface. And now it was procrastinating. Back on Earth, Jet Propulsion Laboratory, JPL, engineers were both worried and stumped. Pathfinder's highest priority task, to move data into and out of its information bus, was mysteriously being neglected as a robot whiled away its time on tasks of middling importance. What was going on? Didn't the robot know any better? Suddenly Pathfinder registered that the information bus hadn't been dealt with for an unacceptably long time, and, lacking a subtler recourse, initiated a complete restart, costing the mission the better part of a day's work. A day or so later, the same thing happened again. Working feverishly, the JPL team finally managed to reproduce and then diagnose the behavior. The culprit was a classic scheduling hazard called priority inversion. What happens in a priority inversion is that a low priority task takes possession of a system resource, access to a database, let's say, to do some work, but is then interrupted partway through that work by a timer, which pauses it and invokes the system scheduler. The scheduler tees up a high priority task, but it can't run because the database is occupied. And so the scheduler moves down the priority list, running various unblocked medium priority tasks instead, rather than the high priority one, which is blocked, or the low priority one that's blocking it, which is stuck in line behind all the medium priority work. In these nightmarish scenarios, the system's highest priority can sometimes be neglected for arbitrarily long periods of time. Once JPL engineers had identified the Pathfinder problem as a case of priority inversion, they wrote up a fix and beamed the new code across millions of miles to Pathfinder. What was the solution they sent flying across the solar system? Priority inheritance. If a low priority task is found to be blocking a high priority resource, well, then all of a sudden, that low priority task should momentarily become the highest priority thing on the system, inheriting the priority of the thing it's blocking. The comedian Mitch Hedberg recounts a time when I was at a casino. I was minding my own business, and this guy came up and said, "You're gonna have to move, you're blocking the fire exit." As though if there was a fire, I wasn't gonna run. The bouncer's argument was priority inversion. Hedberg's rebuttal was priority inheritance. Hedberg, lounging casually in front of a fleeing mob, puts his low priority loitering ahead of their high priority running for their lives, but not if he inherits their priority. And a non-rushing mob has a way of making one inherit their priority rather quickly. As Hedberg explains, if you're flammable and have legs, you are never blocking a fire exit. The moral here is that a love of getting things done isn't enough to avoid scheduling pitfalls, and neither is a love of getting important things done. A commitment to fastidiously doing the most important thing you can, if pursued in a head-down, myopic fashion, can lead to what looks for all the world like procrastination. As with a car spinning its tires, the very desire to make immediate progress is how one gets stuck. Things which matter most must never be at the mercy of things which matter least, Goethe allegedly proclaimed, but while that has the ring of wisdom about it, sometimes it's just not true. Sometimes that which matters most cannot be done until that which matters least is finished, so there's no choice but to treat that unimportant thing as being every bit as important as whatever it's blocking. When a certain task can't be started until another one is finished, scheduling theorists call that a precedence constraint. For operations research expert Laura Albert McClay, explicitly remembering this principle has made the difference on more than one occasion in her own household. It can be really helpful if you can see these things. Of course, getting through the day with 3 kids, there's a lot of scheduling. We can't get out the door unless the kids get breakfast first, and they can't get breakfast first if I don't remember to give them a spoon. Sometimes there's something very simple that you forget that just delays everything. In terms of scheduling algorithms, just knowing what that is and keeping that moving is incredibly helpful. That's how I get things done every day. In 1978, scheduling researcher Jan Carol Lenstra was able to use the same principle while helping his friend Gene move into a new house in Berkeley. Gene was postponing something that had to be finished before we could start something else which was urgent. As Lenstra recalls, they needed to return a van, but needed the van to return a piece of equipment, but needed the equipment to fix something in the apartment. The apartment fix didn't feel urgent, hence its postponement, but the van returned it. Says Lenstra, I explained to him that the former task should be considered even more urgent. While Lenstra is a central figure in scheduling theory and thus was well positioned to give this advice to his friend, it came with a particularly delicious irony. This was a textbook case of priority inversion caused by precedence constraints. And arguably the 20th century's single greatest expert on precedence constraints was none other than his friend, Eugene Lawler. The speed bump. Considering he spent much of his life thinking about how to most efficiently complete a sequence of tasks, Lawler took an intriguingly circuitous route to his own career. He studied mathematics at Florida State University before beginning graduate work at Harvard in 1954, though he left before finishing a doctorate. After time in law school, the army, and, thematically enough, working in a machine shop, he went back to Harvard in 1958, finishing his PhD and taking a position at the University of Michigan. Visiting Berkeley on sabbatical in 1969, he was arrested at a notorious Vietnam War protest. He became a member of the faculty at Berkeley the following year and acquired a reputation there for being the social conscience of the computer science department. After his death in 1994, the Association for Computing Machinery established an award in Lawler's name, honoring people who demonstrate the humanitarian potential of computer science. Lawler's first investigation into precedence constraints suggested that they could be handled quite easily. For instance, take the earliest due date algorithm that minimizes the maximum lateness of a set of tasks. If your tasks have precedence constraints, that makes things trickier. You can't just plow forward and order a due date if some tasks can't be started until others are finished. But in 1968, Lawler proved that this is no trouble as long as you build the schedule back to front, look only at the tasks that no other tasks depend on, and put the one with the latest due date at the end of the schedule. Then simply repeat this process, again considering at each step only those tasks that no other, as yet unscheduled, tasks depend upon as a prerequisite. But as Lawler looked more deeply into precedence constraints, he found something curious. The shortest processing time algorithm, as we saw, is the optimal policy if you want to cross off as many items as quickly as possible from your to-do list. But if some of your tasks have precedence constraints, there isn't a simple or obvious tweak to shortest processing time to adjust for that. Although it looked like an elementary scheduling problem, neither Lawler nor any other researcher seemed to be able to find an efficient way to solve it. In fact, it was much worse than this. Lawler himself would soon discover that this problem belongs to a class that most computer scientists believe has no efficient solution. It's what the field calls intractable. Asterisk scheduling theory's first speed bump turned out to be a brick wall, as we saw with the triple or nothing scenario for which optimal stopping theory has no sage words. Not every problem that can be formally articulated has an answer. In scheduling, it's clear by definition that every set of tasks and constraints has some schedule that's the best, so scheduling problems aren't unanswerable per se, but it may simply be the case that there's no straightforward algorithm that can find you the optimal schedule in a reasonable amount of time. This led researchers like Lawler and Lenstra to an irresistible question. Just what proportion of scheduling problems was intractable, anyway? 20 years after scheduling theory was kick-started by Selma Johnson's bookbinding paper, the search for individual solutions was about to become something much grander and more ambitious by far, a quest to map the entire landscape of scheduling theory. What the researchers found was that even the subtlest change to a scheduling problem often tips it over the fine and irregular line between tractable and intractable. For example, Moore's algorithm minimizes the number of late tasks, or rotten fruits, when they are all of equal value, but if some are more important than others, the problem becomes intractable, and no algorithm can readily provide the optimal schedule. Likewise, having to wait until a certain time to start some of your tasks makes nearly all of the scheduling problems for which we otherwise had efficient solutions into intractable problems. Not being able to put out the trash until the night before collection might be a reasonable municipal bylaw, but it will send your calendar headlong into intractability. The drawing of the borders of scheduling theory continues to this day. A recent survey showed that the status of about 7% of all problems is still unknown. Scheduling's terra incognita. Of the 93% of the problems that we do understand, however, the news isn't great. Only 9% can be solved efficiently, and the other 84% have been proven intractable. In other words, most scheduling problems admit no ready solution. If trying to perfectly manage your calendar feels overwhelming, maybe that's because it actually is. Nonetheless, the algorithms we have discussed are often the starting point for tackling those hard problems, if not perfectly, then at least as well as can be expected. Drop everything. Preemption and uncertainty. The best time to plant a tree is 20 years ago. The second best time is now. Proverb. So far we have considered only factors that make scheduling harder, but there is one twist that can make it easier: being able to stop one task part way through and switch to another. This property, preemption, turns out to change the game dramatically, minimizing maximum lateness for serving customers in a coffee shop, or the sum of completion times for rapidly shortening your to-do list. Both cross the line into intractability if some tasks can't be started until a particular time, but they return to having efficient solutions once preemption is allowed. In both cases, the classic strategies earliest due date and shortest processing time, respectively, remain the best, with a fairly straightforward modification. When a task's starting time comes, compare that task to the one currently underway. If you're working by earliest due date and the new task is due even sooner than the current one, switch gears. Otherwise, stay the course. Likewise, if you're working by shortest processing time and the new task can be finished faster than the current one, pause to take care of it first. Otherwise, continue with what you were doing. Now, on a good week, a machine shop might know everything expected of them in the next few days, but most of us are usually flying blind, at least in part. We might not even be sure, for instance, when we'll be able to start a particular project. When will so and so give me a solid answer on the such and such? And at any moment our phone can ring, or an email can pop up with news of a whole new task to add to our agenda. It turns out, though, that even if you don't know when tasks will begin, earliest due date and shortest processing time are still optimal strategies, able to guarantee you, on average, the best possible performance in the face of uncertainty. If assignments get tossed on your desk at unpredictable moments, the optimal strategy for minimizing maximum lateness is still the preemptive version of earliest due date, switching to the job that just came up, if it's due sooner than the one you're currently doing, and otherwise ignoring it. Similarly, the preemptive version of shortest processing time, compare the time left to finish the current task to the time it would take to complete the new one, is still optimal for minimizing the sum of completion times. In fact, the weighted version of shortest processing time is a pretty good candidate for best general purpose scheduling strategy in the face of uncertainty. It offers a simple prescription for time management. Each time a new piece of work comes in, divide its importance by the amount of time it will take to complete. If that figure is higher than for the task you're currently doing, switch to the new one. Otherwise, stick with the current task. This algorithm is the closest thing that scheduling theory has to a skeleton key or Swiss Army knife, the optimal strategy not just for one flavor of problem but for many. Under certain assumptions it minimizes not just the sum of weighted completion times, as we might expect, but also the sum of the weights of the late jobs and the sum of the weighted lateness of those jobs. Intriguingly, optimizing all these other metrics is intractable if we know the start times and durations of jobs ahead of time. So considering the impact of uncertainty in scheduling reveals something counterintuitive. There are cases where clairvoyance is a burden. Even with complete foreknowledge, finding the perfect schedule might be practically impossible. In contrast, thinking on your feet and reacting as jobs come, it won't give you as perfect a schedule as if you'd seen into the future, but the best you can do is much easier to compute. That's some consolation. As business writer and coder Jason Fried says, feel like you can't proceed until you have a bulletproof plan in place. Replace "plan" with "guess" and take it easy. Scheduling theory bears this out. When the future is foggy, it turns out you don't need a calendar, just a to-do list. Preemption isn't free. The context switch. The hurried-er I go / the behind-er I get needlepoint scene in Boonville, CA. Programmers don't talk because they must not be interrupted to synchronize with other people or their representation in telephones. Buzzers and doorbells can only mean interrupting the thought train. Interruptions mean certain bugs. You must not get off the train. LNULLMAN. Scheduling theory thus tells a reasonably encouraging story after all. There are simple, optimal algorithms for solving many scheduling problems, and those problems are tantalizingly close to situations we encounter daily in human lives. But when it comes to actually carrying out single machine scheduling in the real world, things get complicated. First of all, people and computer operating systems alike face a curious challenge. The machine that is doing the scheduling and the machine being scheduled are one and the same, which makes straightening out your to-do list an item on your to-do list needing itself to get prioritized and scheduled. Second, preemption isn't free. Every time you switch tasks, you pay a price, known in computer science as a context switch. When a computer processor shifts its attention away from a given program, there's always a certain amount of necessary overhead. It needs to effectively bookmark its place and put aside all of its information related to that program. Then it needs to figure out which program to run next. Finally, it must haul out all the relevant information for that program, find its place in the code, and get in gear. None of this switching back and forth is real work, that is, none of it actually advances the state of any of the various programs the computer is switching between. It's meta work. Every context switch is wasted time. Humans clearly have context switching costs too. We feel them when we move papers on and off our desk, close and open documents on our computer, walk into a room without remembering what had sent us there, or simply say out loud, "Now, where was I?" or "What was I saying?" Psychologists have shown that for us, the effects of switching tasks can include both delays and errors at the scale of minutes rather than microseconds. To put that figure in perspective, anyone you interrupt more than a few times an hour is in danger of doing no work at all. Personally, we have found that both programming and writing require keeping in mind the state of the entire system, and thus carry inordinately large context switching costs. A friend of ours who writes software says that the normal workweek isn't well suited to his workflow, since for him 16-hour days are more than twice as productive as 8-hour days. Brian, for his part, thinks of writing as a kind of blacksmithing, where it takes a while just to heat up the metal before it's malleable. He finds it somewhat useless to block out anything less than 90 minutes for writing, as nothing much happens in the first half hour, except loading a giant block of "Now, where was I?" into his head. Scheduling expert Kirk Pruss of the University of Pittsburgh has had the same experience. "If it's less than an hour, I'll just do errands instead, because it'll take me the first 35 minutes to really figure out what I want to do, and then I might not have time to do it." Rudyard Kipling's celebrated 1910 poem ends with an exuberant call for time management. "If you can fill the unforgiving minute / with 60 seconds worth of distance, run if only." The truth is, there's always overhead time lost to meta work, to the logistics of bookkeeping and task management. This is one of the fundamental trade-offs of scheduling. And the more you take on, the more overhead there is. At its nightmarish extreme, this turns into a phenomenon called thrashing. Thrashing. Gage, Mr. Zuckerberg, do I have your full attention? Zuckerberg, you have part of my attention, you have a minimum amount. The social network. Computers multitask through a process called threading, which you can think of as being like juggling a set of balls. Just as a juggler only hurls one ball at a time into the air, but keeps 3 aloft, a CPU only works on one program at a time, but by swapping between them quickly enough, on the scale of 10,000ths of a second, it appears to be playing a movie, navigating the web, and alerting you to incoming ML all at once. In the 1960s, computer scientists began thinking about how to automate the process of sharing computer resources between different tasks and users. It was an exciting time, recounts Peter Denning, now one of the top experts on computer multitasking, who was then working on his doctorate at MIT. Exciting and uncertain. How do you partition a main memory among a bunch of jobs that are in there when some of them want to grow and some might want to shrink, and they are going to interact with each other, trying to steal memory, and all these kinds of things? How do you manage that whole set of interactions? Nobody knew anything about that. Not surprisingly, given that the researchers didn't really know yet what they were doing, the effort encountered difficulties, and there was one in particular that caught their attention. As Denning explains, under certain conditions a dramatic problem shows up as you add more jobs to the multiprogramming mix. At some point you pass a critical threshold, unpredictable exactly where it is, but you'll know it when you get there, and all of a sudden the system seems to die. Think again about our image of a juggler. With one ball in the air, there's enough spare time, while that ball is aloft for the juggler, to toss some others upward as well. But what if the juggler takes on one more ball than he can handle? He doesn't drop that ball, he drops everything. The whole system, quite literally, goes down. As Denning puts it, the presence of one additional program has caused a complete collapse of service. The sharp difference between the two cases at first defies intuition, which might lead us to expect a gradual degradation of service as new programs are introduced into crowded main memory. Instead, catastrophe. And while we can understand a human juggler being overwhelmed, what could cause something like this to happen to a machine? Here scheduling theory intersects caching theory. The whole idea of caches is to keep the working set of needed items available for quick access. One way this is done is by keeping the information the computer is currently using in fast memory rather than on the slow hard disk. But if a task requires keeping track of so many things that they won't all fit into memory, then you might well end up spending more time swapping information in and out of memory than doing the actual work. What's more, when you switch tasks, the newly active task might make space for its working set by evicting portions of other working sets from memory. The next task, upon reactivation, would then reacquire parts of its working set from the hard disk and muscle them back into memory again, displacing others. This problem, tasks stealing space from each other, can get even worse in systems with hierarchies of caches between the processor and the memory. As Peter Zijlstra, one of the head developers on the Linux operating system scheduler, puts it, the caches are warm for the current workload, and when you context switch you pretty much invalidate all caches. And that hurts. At the extreme, a program may run just long enough to swap its needed items into memory before giving way to another program that runs just long enough to overwrite them in turn. This is thrashing, a system running full tilt and accomplishing nothing at all. Denning first diagnosed this phenomenon in a memory management context, but computer scientists now use the term thrashing to refer to pretty much any situation where the system grinds to a halt because it's entirely preoccupied with meta work. Or thrashing computers' performance doesn't bog down gradually, it falls off a cliff. Real work has dropped to effectively zero, which also means it's going to be nearly impossible to get out. Thrashing is a very recognizable human state. If you've ever had a moment where you wanted to stop doing everything, just to have the chance to write down everything you were supposed to be doing, but couldn't spare the time, you've thrashed. And the cause is much the same for people as for computers. Each task is a draw on our limited cognitive resources. when merely remembering everything we need to be doing occupies our full attention, or prioritizing every task consumes all the time we had to do, the more our train of thought is continually interrupted before those thoughts can translate to action. It feels like panic, like paralysis by way of hyperactivity. It's thrashing, and computers know it well. If you've ever wrestled with a system in a state of thrashing, and if you've ever been in such a state, then you might be curious about the computer science of getting out. In his landmark 1960s paper on the subject, Denning noted that an ounce of prevention is worth a pound of cure. The easiest thing to do is simply to get more memory, enough RAM, for instance, to fit the working sets of all the running programs into memory at once, and reduce the time taken by a context switch. But preventive advice for thrashing doesn't help you when you find yourself in the midst of it. Besides, when it comes to human attention, we are stuck with what we've got. Another way to avert thrashing before it starts is to learn the art of saying no. Denning advocated, for instance, that a system should simply refuse to add a program to its workload if it didn't have enough free memory to hold its working set. This prevents thrashing in machines and is sensible advice for anyone with a full plate. But this too might seem like an unattainable luxury to those of us who find ourselves already overloaded or otherwise unable to throttle the demands being placed on us. In these cases, there's clearly no way to work any harder, but you can work dumber. Along with considerations of memory, one of the biggest sources of meta work in switching contexts is the very act of choosing what to do next. This too can at times swamp the actual doing of the work. Faced with, say, an overflowing inbox of N messages, we know from sorting theory that repeatedly scanning it for the most important one to answer next will take N2 operations N scans of N messages apiece. This means that waking up to an inbox that's 3 times as full as usual could take you 9 times as long to process. What's more, scanning through those emails means swapping every message into your mind, one after another, before you respond to any of them, a surefire recipe for memory thrashing. In a thrashing state, you're making essentially no progress, so even doing tasks in the wrong order is better than doing nothing at all. Instead of answering the most important emails first, which requires an assessment of the whole picture that may take longer than the work itself, maybe you should sidestep that quadratic time quicksand by just answering the emails in random order, or in whatever order they happen to appear on screen. Thinking along the same lines, the Linux core team, several years ago, replaced their scheduler with one that was less smart about calculating process priorities, but more than made up for it by taking less time to calculate them. If you still want to maintain your priorities, though, there's a different and even more interesting bargain you can strike to get your productivity back. Interrupt coalescing. Part of what makes real-time scheduling so complex and interesting is that it is fundamentally a negotiation between 2 principles that aren't fully compatible. These 2 principles are called responsiveness and throughput, how quickly you can respond to things, and how much you can get done overall. Anyone who's ever worked in an office environment can readily appreciate the tension between these 2 metrics. It's part of the reason there are people whose job it is to answer the phone. They are responsive, so that others may have throughput. Again, life is harder when, like a computer, you must make the responsiveness/throughput trade-off yourself. And the best strategy for getting things done might be, paradoxically, to slow down. Operating system schedulers typically define a period in which every program is guaranteed to run at least a little bit, with the system giving a slice of that period to each program. The more programs are running, the smaller those slices become, and the more context switches are happening every period, maintaining responsiveness at the cost of throughput. Left unchecked, however, this policy of guaranteeing each process at least some attention every period could lead to catastrophe. With enough programs running, a task slice would shrink to the point that the system was spending the entire slice on context switching before immediately context switching again to the next task. The culprit is the hard responsiveness guarantee. So modern operating systems in fact set a minimum length for their slices and will refuse to subdivide the period any more finely. In Linux, for instance, this minimum useful slice turns out to be about 3/4 of a millisecond, but in humans it might realistically be at least several minutes. If more processes are added beyond that point, the period will simply get longer. This means that processes will have to wait longer to get their turn, but the turns they get will at least be long enough to do something. Establishing a minimum amount of time to spend on any one task helps to prevent a commitment to responsiveness from obliterating throughput entirely. If the minimum slice is longer than the time it takes to context switch, then the system can never get into a state where context switching is the only thing it's doing. It's also a principle that is easy to translate into a recommendation for human lives. Methods such as time boxing or Pomodoros, where you literally set a kitchen timer and commit to doing a single task until it runs out, are one embodiment of this idea. But what slice size should you aim for? Faced with the question of how long to wait between intervals of performing a recurring task, like checking your email, the answer from the perspective of throughput is simple: as long as possible. But that's not the end of the story. Higher throughput, after all, also means lower responsiveness. For your computer, the annoying interruption that it has to check on regularly isn't email, it's you. You might not move the mouse for minutes or hours, but when you do, you expect to see the pointer on the screen move immediately, which means the machine expends a lot of effort simply checking in on you. The more frequently it checks on the mouse and keyboard, the quicker it can react when there is input, but the more context switches it has to do. So the rule that computer operating systems follow when deciding how long they can afford to dedicate themselves to some task is simple: as long as possible without seeming jittery or slow to the user. When we humans leave the house to run a quick errand, we might say something like, "You won't even notice I'm gone." When our machines context switch into a computation, they must literally return to us before we notice they're gone. To find this balancing point, operating systems programmers have turned to psychology, mining papers in psychophysics for the exact number of milliseconds of delay it takes for a human brain to register lag or flicker. There is no point in attending to the user any more often than that. Thanks to these efforts, when operating systems are working right, you don't even notice how hard your computer is exerting itself. You continue to be able to move your mouse around the screen fluidly, even when your processor is hauling full tilt. The fluidity is costing you some throughput, but that's a design trade-off that has been explicitly made by the system engineers. Your system spends as much time as it possibly can away from interacting with you, then gets around to redrawing the mouse just in time. And again, this is a principle that can be transferred to human lives. The moral is that you should try to stay on a single task as long as possible without decreasing your responsiveness below the minimum acceptable limit. Decide how responsive you need to be, and then, if you want to get things done, be no more responsive than that. If you find yourself doing a lot of context switching because you're tackling a heterogeneous collection of short tasks, you can also employ another idea from computer science: interrupt coalescing. If you have 5 credit card bills, for instance, don't pay them as they arrive. Take care of them all in one go when the 5th bill comes. As long as your bills are never due less than 31 days after they arrive, you can designate, say, the 1st of each month as bill paying day, and sit down at that point to process every bill on your desk, no matter whether it came 3 weeks or 3 hours ago. Likewise, if none of your email correspondence require you to respond in less than 24 hours, you can limit yourself to checking your messages once a day. Computers themselves do something like this. They wait until some fixed interval and check everything, instead of context switching to handle separate, uncoordinated interrupts from their various subcomponents on occasion. Computer scientists notice the absence of interrupt coalescing in their own lives. Says Google Director of Research Peter Norvig, "I had to go downtown 3 times today to run errands, and I said, oh, well, that's just a one-line bug in your algorithm. You should have just waited, or added it to the to-do queue, rather than executing them sequentially as they got added one at a time." At human scale, we get interrupt coalescing for free from the postal system, just as a consequence of their delivery cycle. Because mail gets delivered only once a day, something mailed only a few minutes late might take an extra 24 hours to reach you. Considering the costs of context switching, the silver lining to this should by now be obvious: you can only get interrupted by bills and letters at most once a day. What's more, the 24-hour postal rhythm demands minimal responsiveness from you. It doesn't make any difference whether you mail your reply 5 minutes or 5 hours after receiving a letter. In academia, holding office hours is a way of coalescing interruptions from students And in the private sector, interrupt coalescing offers a redemptive view of one of the most maligned office rituals, the weekly meeting. Whatever their drawbacks, regularly scheduled meetings are one of our best defenses against the spontaneous interruption and the unplanned context switch. Perhaps the patron saint of the minimal context switching lifestyle is a legendary programmer Donald Knuth. I do one thing at a time, he says. This is what computer scientists call batch processing. Their alternative is swapping in and out. I don't swap in and out. Knuth isn't kidding. On January 1st, 2014, he embarked on the TAYONGTONG loop of 2014, in which he fixed all of the bugs that had been reported in his TAYONGTONG typesetting software over the previous 6 years. His report ends with the cheery sign-off, "Stay tuned for the TAYONGTONG loop of 2021. Likewise, Knuth has not had an email address since 1990. Email is a wonderful thing for people whose role in life is to be on top of things. But not for me. My role is to be on the bottom of things. What I do takes long hours of studying and uninterruptible concentration." He reviews all his postal mail every 3 months, and all his faxes every 6. But one does not need to take things to Knuth's extreme to wish that more of our lives used interrupt coalescing as a design principle. The post office gives it to us almost by accident. Elsewhere, we need to build it, or demand it, for ourselves. Our beeping and buzzing devices have do not disturb modes, which we could manually toggle on and off throughout the day, but that is too blunt an instrument. Instead, we might agitate for settings that would provide an explicit option for interrupt coalescing, the same thing at a human timescale that the devices are doing internally. Alert me only once every 10 minutes, say, then tell me everything. If you enjoyed this video and want to hear it again, be sure to click the subscribe button. And also click the notification bell to switch between getting all notifications, and like and share. Leave your comment and suggestions below. Thank you for watching.